Hello. Okay. So we are studying renormalization. And in the last lecture, we demonstrated how the counterterm Lagrangian has to be found order by order in the lambda expansion. And we calculated it. The result, so let me now define, I will get back to the result of the counterterm Lagrangian in a while. Define renormalized Lagrangian. Which is the original Lagrangian, the classical Lagrangian plus the counterterm Lagrangian that we had added. And this counterterm Lagrangian has the form half a del mu phi plus half m square b phi square plus lambda by factorial 4 mu to the power epsilon c phi to the power 4. And we calculated a, b, c. So let's get to the result. So this is the result that we found last time. So this is the counterterm Lagrangian that we found earlier, and you see that this has this kind of a form. We have the same terms of the original Lagrangian, but now with the different coefficients a, b, and c, where a, b, and c are given by these expressions. Okay, so there should be a -1 here, so there's some typos. And this is epsilon. So let me copy this part. This is A. Then B is given by this expression. So this A begins with order lambda square and then higher order in lambda term. B begins with order lambda and then lambda square and then higher order in lambda. Then we have 1/4 lambda by factorial for mu to the power epsilon times c times pi to the power 4. So c is given by this expression. Okay, so now what we can do, since the original Lagrangian has the same form as the counter term Lagrangian, we can write renormalized Lagrangian in the following form. Where I have added the original terms in L with this, since they have the same form, it's just going to change the coefficients. So for example, in the kinetic term in L has half times del mu phi, and the counter term has an additional coefficient A. So the renormalized Lagrangian has the term half del mu phi with a coefficient 1 plus A. And that 1 plus A factor can be, so since it's A is position independent, so is a constant, that 1 plus A can be absorbed inside phi, and that defines phi 0. And therefore, where phi 0 is equal to 1 plus A to the power half phi, this factor 1 plus A to the power half is also called z phi to the power half. 1 plus A is z phi. It's called wave function renormalization. Similarly, m0 square is given by this coefficient is the original Lagrangian has half m square phi square term, and then counter term has a coefficient, same term with a coefficient b, so the net coefficient is 1 plus b, but then phi has to be expressed in terms of phi 0. Therefore the m0 is related to m in this following manner: 1 plus b divided by 1 plus a. In other words, 1 plus b times z phi to the power minus 1 m square. Similarly, lambda 0 is given by 1 plus c divided by 1 plus a whole square, because this term has phi to the power 4, two powers of phi extra. So then there is 1 plus a whole square times lambda mu to the power epsilon, which is same as 1 plus c times z phi to the minus 2 times lambda mu to the epsilon. Now, of course, since we are including this mu to the power epsilon term inside lambda 0, this lambda 0 is dimensionful. It's not dimensionless. So lambda 0 is dimensionful. And So we see that this is called bare Lagrangian, or renormalized Lagrangian is of the same form of the original Lagrangian, and the quantities that we are defining now, phi0, m0, and lambda0, these are called bare quantities, and which are divergent because this A, B, and C are the counter terms which diverge in the epsilon going to 0 limit because of the poles. They also depend on the finite ambiguities, F, G, and H coefficients, but they diverge. So these are called bare quantities. And which are divergent as epsilon goes to 0. Similarly, we have these other quantities, phi, m square, and lambda. These we will be calling as renormalized quantities. These are finite as epsilon goes to 0. So the original Lagrangian, this form, the classical Lagrangian, can be viewed as given by, as written in terms of, I mean, we can interpret the classical Lagrangian as if it is written in terms of the bare quantities, phi0, m, bare field, and bare parameters, m0 square and lambda 0. And they are written in terms of the renormalized quantities, which are finite, and the bare quantities are divergent. Now one can relate this relation phi0, the bare quantities versus the renormalized quantities, and these relations can be written in different manner. So I will write down this relation in two different ways. Let us first notice that, so relation 1, one can write lambda 0 as mu to the power epsilon, which is the dimension, times, let me write and then explain, a0 lambda m by mu epsilon. So what I have done is that apart from the scale, I have written the rest of the part of the expression as expansion in epsilon poles. So there is a part which is which have the epsilon poles, and the poles go from 1 to order go from 1 to infinity, and each pole has a coefficient, and that coefficient depends on lambda and mu by epsilon. Earlier I was writing it as a lambda expansion, now I'm writing as a pole expansion. And of course AK, both AK, BK and CK, each one of them will have a lambda expansion, right? Because we are doing the perturbative calculations. And apart from that, apart from the poles, there are finite pieces, and these are given by A0, B0 and C0. Now let us look at the finite contributions here. So A, B, and C, they have finite contributions. For example, at lambda hat square order, it has H2. B has F1, G1, and F2, and C has G1 at this order. So at higher orders, when you add new counter terms, each one of them will have, at every order, you will have additional finite pieces. So you end up getting a set of finite ambiguities, Fi, Gi, and Hi. Each one of them depend on epsilon and m hat square, and such that in the limit epsilon going to 0, all of them are finite, right? That is what the finite ambiguities are. Now, so these finite ambiguities will be involved in these finite pieces, and that is the source of the m dependence. That's m by mu ratio appears here in the argument. They are coming from these finite pieces, because these finite pieces are dependent on m hat. M hat is m, I think, m by m square by 4 pi mu square. M hat square is m square by 4 pi mu square. So this is the source of m dependence of this A0, B0, C0 coefficients. And the pole coefficient, the residues, they at this order, we don't see them to be dependent on m hat. We have just a constant piece here, in here, here, and here. However, as I explained in the previous lecture, that when you go to higher order terms, sufficiently high order terms, then you are basically taking bigger diagrams. And in these bigger diagrams, you will have overlapping expressions, in the sense that finite piece coming from one loop, so there will be overlapping loops where each one will be given by some pole term plus a finite term, and that will be multiplied by an expression of the same sort coming from another loop. And therefore this finite part will be multiplied with the pole terms, giving rise to pole terms in the final expression, which have coefficients as lower order finite pieces. So that is why these residues here in general will have m dependence coming from the finite pieces. Okay, that is the explanation. So of this kind of an expression, of this kind of a way of writing this relation between the bare and renormalized quantities. So let me note it down here. So if you set this finite ambiguities to be 0, then this AK, BK, and CK, this bunch of all this for all values of K will become independent of the mass parameter. Now, another way of writing this relation is lambda 0 can be written as lambda times mu to the power epsilon times, say, x, which depends on lambda m by mu and epsilon. And this has a form, it starts with 1 and then lambda times, this is the lambda expansion form, lambda square times something and so on. Similarly, m0 square can be written as m square times y lambda m by mu and epsilon. And this also has the same lambda type of expansion. And these coefficients of different orders in lambda will have poles in epsilon. This is the original way we got when we did the calculations. This is the original way this is the way we got the expressions originally. And now we could consider lambda to be parametrically small and invert such relations. So consider lambda to be parametrically small and invert the above relations, then you can write you are writing lambda in terms of the lambda and m square in terms of the bare quantities. Then the expression would look like lambda 0 mu to the power minus epsilon x inverse, which is the inverse function of x, they depend on lambda 0 m0 over mu epsilon. Similarly, m square can be written as m0 squared times y inverse lambda 0 m0 by mu c epsilon. Now, this renormalized the Lagrangian. In this Lagrangian, we can interpret this as having no mu dependence. Lambda 0 is, of course, dimension full, but there is no mu dependence, explicit mu dependence in this. So we consider phi 0, the bare quantities, to be independent of mu, but renormalized quantities to be dependent on mu. This is how we are going to interpret this mathematical structure. Okay, this is a crucial point in understanding the mu dependence. Mu is a scale dependence of the renormalized quantities, because we are considering the bare quantities to be mu independent, because you write the Lagrangian in this form and there is no mu. This is how we are defining the problem. Now, considering bare quantities, to be mu independent, the above relations show that lambda m square have implicit dependence on mu. Yeah, this is the relation which we interpret as having lambda as lambda having a mu dependence, because lambda 0 m0 are mu independent. So mu is an arbitrary scale mass parameter. So there are now, you see, after getting to this structure, what we should appreciate is the fact that this counter term cancellation of the divergences, when we introduce that, this is something that is true for all types of regularization, that when we say that there's a UV divergence, the divergence comes from infinite momentum region, and this does not depend on a scale. This fact is not dependent on a scale. If you calculate those integrals, because at the large value of the momentum, infinitely large value of the momentum, the contribution to the integral will diverge. Now, when you regularize it, that means in some sense you are setting a scale so that you are not allowing the contribution coming from the large momentum, but you are only taking contribution coming from certain value of the momentum, certain upper limit of the momentum. In dimensional regularization, it's not easy to see what is the cutoff in the momentum that you are using, but we must be doing something like that, because the divergence comes from the large value of the infinite value of the momentum, and those divergences are written as poles, and the poles are getting cancelled, and therefore we are basically throwing away large value momentum contributions, and that's the origin of the fact that there is a scale involved in this process. So there are two aspects of this process. There's a scale involvement of a scale, which is this mu here, and there is no, right now, whatever I just said, that the scale in the procedure is introducing a scale, how that scale is related to mu, but we'll see that mu is that scale as we go ahead with the discussion. Then this is one feature, that there is a scale, and this other feature is that the scale is arbitrary though, and the other feature is arbitrary finite quantities that are introduced through the counter terms. Okay, so the set of finite ambiguities. So there are two arbitrary things involved. One is mu, and the other is a set of finite ambiguities in the counter terms. And the interpretation of the quantum field theory that is being developed here is going to relate these two arbitrariness in a certain manner. So to do that, let us study the mu dependence of the renormalized 1 pi vertices. But let me finish it here. I will do that in the next slide.